Did you know that if you stand atop the Shard, the tallest building in London, you can look southwards and see France on a clear day? When the air is clear, it would appear to be empty and transparent, but air is far from empty. Right now, the air around you contains approximately 10 trillion atoms per cubic metre. That's a lot of atoms. If you want to get emptier, you have to go higher. At about 100 kilometres above Earth's surface, the number of atoms drops to about 1 million trillion. About a third of the way to the Moon, there are 7 million atoms, and to get much lower, you have to leave the solar system altogether. Interstellar space, which is the space between star systems, contains about 1,000 atoms per cubic metre. If you travel even further and go to the space between galaxies, the count drops to just 10 atoms per cubic metre. The space between galaxies is massive and sparse, but that space is often part of something bigger, situated along chains of galaxies carved out by galaxy filaments, the long arms of galaxies which can branch for hundreds of millions of light years. These filaments group into concentrated areas called galaxy superclusters, and when viewed on a wide enough scale, they all sort of connect. But what about the space between filaments, the gaps between large-scale galactic structures? Well, these spaces are just about as remote and empty as you can get in the universe, and we have a fitting name for them: voids. We are so fascinated by other galaxies and what could exist elsewhere that we often overlook the significance of the voids in between. They are a component of the universe itself, and they've taught us a great deal about areas ranging from galaxy superstructure formation to the expansion of the universe itself. And today we're going to revisit some of that knowledge as we head into the void. The contents of the macro universe can be broken down into two structural components: walls, where matter exists in abundance, and voids, the space in between. A void is a vast, somewhat spherical region of space with a low cosmic density. We measure cosmic density by physical galaxy counts as opposed to estimations of mass, so the technical definition for a void references an area with a low number of galaxies, approximately 1/10 of the typical number inside walls, according to the widely accepted definition. Whereas galaxy walls are composed of gravitationally bound structures and filaments, voids are not technically structures. They are the vast spaces between the structures, but are nonetheless a fundamental property of the universe. Voids can exist both inside galactic walls and in the spaces between them. The smallest are about 10 megaparsecs in diameter, with a megaparsec being equal to roughly 3.2 million light-years, meaning typical voids are usually at least 30 million light-years wide. Larger typical voids can reach up to 10 times that size, giving them a whopping diameter of around 300 million light-years, or 100 megaparsecs. And at that size, we have another name for them: supervoids. But they can get even larger still. Voids which form inside galaxy walls are smaller than voids that form in the low-density spaces of the universe. These empty spaces can be much bigger, with some of the largest areas we've found over 1 billion light-years in diameter. It's hard to appreciate just how large that scale is. There's no absolute ratio for the share of galaxy walls and voids in the universe, but what we do know is that the vast majority of its volume is made up of these massive near-empty spaces of low cosmic density. Cosmic voids became a branch of study in astrophysics in the 1970s, when redshift surveys became more common. By the end of the decade, voids had been identified in the foreground of the Coma cluster and the A1367 cluster. Redshift surveying technologies have come a long way since then, and it wasn't long before we were mapping our universe in exquisite 3D detail for the first time. By the 1990s, 3D redshift surveys, such as the Las Campenas survey, were identifying and confirming an abundance of voids throughout the observable universe, and today we have catalogued hundreds of them. Our nearest is the local void, which starts at the edge of our local galactic group and extends over 200 million light-years into the darkness. Voids have existed for as long as the universe. This is because during the first trillionth of a second of time, our universe was tiny and its contents was under unimaginable pressure. Within this ultra-dense primordial soup, quantum fluctuations were causing ripples, and then the universe suddenly expanded violently in an event known as cosmic inflation, and went from microscopic to immeasurable. Like a snapshot of the tiny universe, the contents of the universe as it was in that moment was radically elongated, and the tiny acoustic ripples now propagated across massive cosmic distances, leading to the universe's early plasma, from which the first particles formed, being more concentrated in certain areas and less dense in others. Within the dense areas, structure formation began to occur. First, dark matter began pulling together into massive but diffuse filaments over hundreds of millions of years. And then, baryonic matter traced its path. Subatomic particles became atoms, and atoms became gas clouds, and clouds became stars. The stars collected into groups which formed the first galaxies, and the galaxies moved into clusters, which became superclusters. The scale really is incredible. These structures now interlink to form a massive, sponge-like path over the entire universe, the cosmic web. As all of this took place, the areas of lower density from cosmic inflation were emptied out, and now exist as massive voids between galaxy walls. For this reason, those massive primordial spaces between walls really are empty. Hundreds of millions of light years devoid of not just normal matter, but dark matter as well. It all grouped together in filaments in the early universe and cleared out incomprehensible gaps in the space in between. We don't really know how big these voids can get, and new discoveries continue to push the benchmarks. In contrast, voids which occur inside galaxy walls form as gravitationally bound galaxies are pulled towards one another, which empties out the surrounding space as they converge. The more galaxies merge, the stronger their overall influence, which attracts more galaxies, and so this process is self-reinforcing. This leads to denser clusters and emptier voids. And in fact, when voids form like this, if two form relatively close to each other, a snowball-like effect can lead to something remarkable. While supervoids may be somewhat of a less glamorous area of astronomy, one which has continued to attract particular online attention is the Great Boötes Void, which lies on the edge of the Hercules supercluster. This void is enormous, estimated to be between 250 million and 330 million light-years in diameter and over 200,000 cubic megaparsecs in volume. Upon its discovery, scientists disputed whether there had been enough time since galaxy structures began forming to allow a void of this size to exist, but as it turns out, the Boötes Void isn't actually that unusual or unexpected, and the key to understanding why is hidden in the distribution of a few dozen galaxies within. 60 isolated galaxies exist within the void where thousands would usually be expected, and they make up a tube-like formation near the centre. Scientists now think that this tube may be what's left of the boundaries of two smaller voids, which merged as they grew into one another. The near-perfect spherical shape of the void is the result of a soap bubble-like effect as they merged, and two large voids combined into one massive void, leaving the galaxies on the edge of each stranded inside this new supermassive cosmic abyss. In addition to its size, the Boötes Void is also thought to be one of the sparsest and most eerily empty of its kind. To put the 60 galaxies into some sort of perspective, it's like driving from coast to coast of the United States and passing only a couple of towns on your way, and this doesn't even take into account that the void is three-dimensional. As such, it's earned itself the nickname the Great Nothing, which has been puzzling astronomers since its discovery in 1981. It's so enormous that even light takes hundreds of millions of years to reach the galaxy's inside, and for light leaving the galaxies to reach the outside. In fact, astronomer Greg Aldering at the University of Minnesota said that if humanity had evolved on a world within one of these few dozen central galaxies, we wouldn't have known that other galaxies existed until the 1960s. Imagine scientists in the 60s trying to work that one out. Another thing that voids have helped us to slightly better understand is the mechanism of dark energy, the big unknown force which is pushing the universe apart and speeding up its expansion as it goes. Dark energy expands the universe in all places at once, and not just at the edges. Every part in space grows at the same rate. This means that the swathes of empty space inside the voids of the universe are also growing, pushing the edges outwards, causing them to increase in size as the universe ages. Because we now know that the size, shape and evolution of large voids is partly due to the expanding space within, we can use them to test our current estimations of dark energy's abundance. The simultaneous existence of the largest voids we see in the universe today requires about 70% of the universe's energy density to be dark energy, a figure which is relatively consistent with our measures of the cosmic microwave background, which is a good sign from a research standpoint at least. Another thing we can use the cosmic microwave background for is measuring baryonic acoustic oscillation patterns, aka the distribution of normal matter and energy across the universe. On this map, the warmer areas correlate to filaments and the cooler areas correlate to voids and supervoids. All of this aligns with and reaffirms our current understanding except in one place, the WMAP cold spot. In the early 2000s, an area of the CMB which was unusually cold in comparison to its surrounding areas was identified in the direction of the constellation of Eridanus. It's not the temperature of the area itself that's so unusual, but the difference in temperature between it and the relatively warm ring around it. The temperature deviates by about 70 microkelvin, whereas mean temperature variations are usually just under 20 microkelvin or so, and in some places the temperature varies by as much as 140 microkelvin. This was a puzzling discovery, but it quickly became a big mystery of astrophysics in 2013, when the Planck satellite also detected the cold spot, ruling out any chance of it being a WMAP error. This thing actually exists somewhere out there, but what is it? Well, a group of scientists came out and proposed that a supervoid could in fact be responsible. If this hypothetical Eridanus supervoid exists, then it is probably at least 500 million light years in diameter, and could be as large as 1 billion light years, totally dwarfing even the Boötes void. There is no concrete explanation for the cold spot as of yet, and different studies since then have found conflicting results pertaining to the supervoid hypothesis, but nothing really substantial for or against it yet. And so, while it may not be a supervoid, for now at least, the cold spot is yet another perplexing and fascinating mystery of our universe. Okay, so enough theories and hypotheses. How about a real example of a mind-blowing void which has significance to us? Well, this is where the elasticity of the term void comes into play. Obviously, when you think of a void, you think of a massive virtually empty area, like the Boötes void, or a completely empty gap between galaxy walls. However, because the term refers to a lower than expected number of galaxies, voids can contain clusters and even superclusters of galaxies and still have this apparent underdensity. As it so happens, the largest known void in the universe contains such galactic structures, the largest void which you happen to be sat in the middle of right now. It might sound crazy, but the KBC Void is the largest known void by definition in the entire observable universe, with a lower than expected concentration of galaxies across a roughly spherical expanse of nearly, wait for it, 2 billion light years. And yet, it contains you and I, the planet, the galaxy, the local galactic group, and even a large chunk of the Laniakea supercluster, which is home to no less than 100,000 galaxies. So it's not that exciting when you think about it really, but what is interesting is that we are fairly close to the centre, relatively speaking. While this position doesn't have any implications for our existence that we know of, it does have implications for our observations of the universe around us. Our position in comparison to the rest of the universe is like living in a remote rural town instead of a city, except the cities are gigantic galactic walls. Because these cities of galaxies are denser than us, they are exerting a gravitational influence on us, pulling us through the void and towards the filaments very slowly. This movement may actually be interfering with our measurements of redshift values, and has probably led to some inaccurate estimations in our calculations of the Hubble constant, our measure of the rate at which the universe is expanding. This might explain why the figure we get from analysing redshift values of galaxies around us to determine the Hubble constant is different to the figure we get from analysing the CMB, which would mean that analysing the cosmic microwave background, or echo of the Big Bang, is a more accurate means to study the expansion of the universe, from our perspective at least. If anything, the KBC Void shows us that not all voids really live up to the image of one. We are simply situated in a less dense region of space, like being out in the intergalactic countryside of the universe. The only noticeable side effect this has for us is that our night sky is a bit darker than it might be on planets within galaxy walls, but it's certainly a lot less creepy than it would be if we were in the centre of, say, the Boötes void. Just imagine what it would be like in one of its isolated galaxies within. In the future, when the universe is so large that all other galaxies have receded from view, everywhere that isn't gravitationally bound will expand into its own massive isolated pocket of the universe, leaving unfathomably large voids in the space in between each individual galaxy. And in the distant future, when entropy reaches maximum, no structures will remain, making the universe one indescribably enormous cosmic void. Huge swathes of emptiness in space are a natural property of the universe, which always have been and always will be. But just because they're empty doesn't mean they can't be interesting.